Hello, welcome, welcome to learning OCaml. Um, Ever since I began to stream on Twitch, I kind of, started to stream and the thing goes on. But now when I actually wanted to record this and not stream, and now the vibe again is, different because I kind of started to record this and then I said something and then I wanted to record it again and then I said something, and that's kind of, silly. So I'll just start and, try to be sincere with this. Okay, why OCaml? This is, I think this is, I want to be fair to them. This is with the dark mode on. So without the dark mode, we have a nice, this looks much better actually without the dark mode. I'll turn on the dark mode when it's needed. Why OCaml? You know why? Because first of all, they have a great website. That's important. Well, it's not really that important, but it tells you something but the main thing why I want to learn OCaml is because it's somehow on the fringe, because they have a lot of learning materials which are free, which is great. And a lot of the courses I saw from Cornell, then Harvard CS 51, which is actually the next course after the famous CS 50, and a couple of even more universities, they actually use OCaml to teach. Maybe that's like the new scheme on in universities. It's interesting that there are also Haskell courses, but it's interesting that it seems like on the first, when you just look at it, it seems there are actually more universities offering OCaml courses, but maybe I'm just mistaken. It's just something it kind of feels like, but it's probably not true. So they have a really nice website, and the language has somehow best of both worlds, so it's functional. And I think it can be also lazy if you enable some things, which is cool. And it's imperative as well. So, and lately I've been, trying to learn C programming and to learn about memory allocation and such. So, but I miss kind of working at the same time to learn OCaml. I mean, to learn some kind of functional language. And it's just because I know it's important to do one thing and to do it well, but I kind of like to do more things at the same time. I guess it's just the way I learn. I think it's good. So I also want to be doing, while I learn C, to also do OCaml at the same time. And I will be recording this. There's some noise actually on the sound, so I kind of hope to fix that noise. I'll try to fix it in Audacity maybe. Yeah, I'll see how that will sound. So it's really nice when I have these foundations for beginners, introduction, a tour, your first OCaml. Look at this. And it kind of feels that they're whole built kind of a thing. So the format here, the package manager, and the REPL. I mean, kind of the entire language tools. It's just something what seems to me when I look at it, they kind of seem to be more compact than, for example, Haskell, that has kind of a lot of tools, but maybe it might feel more, what's the word? Fragmented. get started. So if we go here to learn, we have explored the OCaml documentation, jump to beginners section, foundations for beginners, and recommended books. So they have a lot of, look at this, see more books. And here you can choose a language. Well, I'll just choose English, free or paid. So I'll go free. And there are a lot of nice books. So OCaml programming, a textbook on functional programming used at Cornell for third semester programming course, read online. They're really nicely written. I gave it like a programming well, abstraction and design in computation. You read online and real world OCaml. So it's all free stuff, and this is really objective OCaml. Is this new? Because this is kind of the old cover what O'Reilly used. Développement de application avec objectif CAML. Yeah, I think it was actually developed in France. I'm not sure. Read online, think OCaml. So maybe OCaml from the very beginning. So John Whitington takes a no prerequisite approach to teaching a modern general purpose programming language. Each small self-contained chapter introduces a new topic, building until the reader can write quite substantial programs. There are plenty of questions and, crucially, worked answers and hints. So OCaml from the very beginning will appeal both to new programmers as experienced programmers eager to explore functional languages such as OCaml. Maybe OCaml is the best first language that kind of it's not, that brings all the best from the functional realm and also from the imperative. I'm not sure if OCaml does memory allocation, which is kind of the point why I'm doing C. But okay, let's see. It is suitable both for formal use within an undergraduate or graduate curriculum and the interested amateur. So I'm going to go read online. And Amazon, free of charge, PDF, HTML. And now I'm going to put the dark mode on, actually. Okay, so OCaml from the very beginning. Did I press something? I did. So a book for those new to programming, or new to functional programming, or just new to OCaml. That's me, all right. I'm not really new to it, but I'm kind of new to it because I still haven't learned it. Okay. Preface, getting ready, starting off, and there is actually a sequel. So let's go to preface. Actually, let's start from the beginning. This book is based on the author's experience of teaching programming to students in the University of Cambridge supervision system. In particular, working with students for the first year undergraduate course Foundations of Computer Science based on standard ML, and lectured for many years by Lawrence C. Paulson. Yeah, also on YouTube there are a couple of, that's kind of interesting. There is the functional programming course. I think that's actually at Cornell. Is that at Cornell? My CPU is very slow when I'm recording. Yeah, C programming. So, advent of code. This is cool. Yeah, what was I going to look for? Playlists, Linux. Where did I keep it? Writing in OS. These are just some of the playlists I saved. MIT, no. Computer structures, fall. Operating Rust OS. Music. I think I changed it to Logic Foundation. Principles here. Brandon Wu. This thing. So Carnegie Mellon. That's not Cornell. Or Carnegie Mellon. I'm not sure how you read this. Is it like that rich guy? I don't know. So all the lecture videos. This is also nice. I'm not sure what book they use, but it seems like really nice. And Brandon Wu is he's very young. I think he just graduated like last year or something, which is kind of cute because he has this very nice, relaxed style. I really like. So yeah, so check that out. I'll put that in links actually. I'll put that in links. Now I should install also some packages for OCaml. I haven't installed a thing, and I'm on Nixos, so I'm going to open my configuration.nix. Oh. Wait a second. Sudo, no, it's wrong. Sudo-ehx, right. Like this. Oh my, I have to, just a moment, play sound, please. No, don't play sound. Okay. So let's add actually OCaml stuff. And so that I can install it. So OCaml packages. Do I have to add the OCaml packages to everything? Can I just do OCaml? I think I can do OCaml. Dune 3. Or maybe I'll just copy and paste this actually, OCaml packages format. Yeah, this would be nice if I wouldn't have to. Oh, I have plus now. Let's keep it like this. This isn't really okay. OCaml LSB, right. Let's see if that works. Now I'm going to rebuild. I haven't done this yet, so I'm not sure if it's going to work. So it did work. So let's wait until it installs. And in the meantime, maybe let's, start reading. But there is also the OCaml.org/play, where you can try stuff out here, Discuss with the community, watch OCaml videos. So what do they have? They have a subreddit. Development is on GitHub, which is nice. Chat, Discord, IRC chat, Matrix, OCaml Lang, chat in the OCaml Lang, Twitch, live streams about Twitch, yeah, YouTube, Twitter, nice. Maybe I should stream this. Yeah, I'm not sure. Maybe I should. um, okay, did that install? It's installing. Cool. So where is the book? It's here. So an interesting aspect of supervising students from a wide range of backgrounds, some with no previous experience at all, taking computer science as an additional subject within the Cambridge Natural Sciences curriculum, and some with a great deal of programming experience already, is the level playing field which the ML family of languages like OCaml provide. Sometimes those students with least prior programming experience perform the best. I have tried to write a book which has no prerequisites and with which any intelligent undergraduate ought to be able to cope, whilst trying to be concise enough that someone coming from another language might not be too annoyed by the tone. So what I said before, I really like that more than one book. It's kind of, it doesn't just talk about the language, but the books, what they write here, and kind of the general approach is to teach programming principles and stuff like that, which is very nice, and it's free. Special note to those who have already written programs. When I was a boy, our class was using a word processor for the first time. I wanted a little for my story, so I typed it on the first line, and then placing the cursor at the beginning, held down the space bar until the title was roughly in the middle. My friend taught me how to use the centering function, but it seemed more complicated to me, and it stuck with the familiar way. After all, it worked. Later on, of course, when I had more confidence and experience, I realized he had been right. Oh, I see. Yeah, he was typing the space bar until until you get to the middle, but you really don't get to the middle, right? Then you look at the right, then you look at the left, and kind of the middle could be here, but it's much better with a centering function. Yeah, it's much better, because then you don't have to fix it, if your word is too long, because you have to set the right amount of letters, and then, yeah. When starting a language which is fundamentally different from those you have seen before, it can be difficult to see the advantages and to try to think of every concept in terms of the old language. I would urge you to consider the possibility that, at the moment, you might be the boy holding down the spacebar. Ooh, nice. I like this, change of roles. Inevitably, the approach here owes a depth to that taken by Lawrence C. Paulson, both in his lecture notes and in his book ML for the Working Programmer. Question 3 in chapter 11 is inspired by the examination question of his. I was taught Standard ML by Professor Paulson and Andrei Seriantov in autumn 2000. Mark Shinwell has been a constant source of helpful discussion. Robin Walker and laterly Andrew Rice have arranged the supervision system at Queen's College, within which I have taught since 2004. I'm grateful to the developers of OCaml who have provided such a pleasant environment in which to write programs. Helpful comments on the earlier draft were provided by Martin Di Meglio, Damien Dominguez, Arthur Guillon, Zichan, Robert Jacob, Xavier Leroy, Florent Monnier, and Benjamin Pierce. Benjamin Pierce, I know that name. He wrote like that famous book on types. And of course, I thank all my students, some of whom are now working with OCaml for a living. Yeah, I think that's not so, OCaml is not so used in the industry, but I'm gonna put this thing on. Or maybe like this. kind of coldish. So a book for those new to programming or new to functional programming. So I think we just read this, right? Getting ready? Okay. This book is about teaching the computer to do new things by writing computer programs. Just as there are different languages for humans to speak to one another, there are different programming languages for humans to speak to computers. We're going to be using a programming language called OCaml. It might already be on your computer, or you may have to find it on the internet and install it yourself. You will know that you have OCaml working when you see something like this. OCaml. What do you mean, OCaml? Do I just press OCaml? OCaml. Now, I do have Helix. I should probably... How do I quit? No. Exit. No. Control C. No. You see, you don't know. You see, I don't know how to quit now. Exit. Yeah. OCaml. Exit. Exit. Yeah. Okay. So let me check the health. OCaml. I just want to check if my editor, even though that's not so important for now. Look at this, OCaml LL. Oh, he already found it. That's really sweet. Yeah, wait, what's the last text object? Wow. All right, Helix. Okay, let's go to OCaml. Oh, it does not have the Control L, like clear screen. Okay, so it was exit like this. Let's do now OCaml. Okay, so OCaml is waiting us to type something. Try typing 1 plus 2. Let's write 1. It says that it's an int, 2. So I guess we always have to do this semicolon. What if we don't press semicolon? This expression has type int. This is not a function. It cannot be applied. I like the error messages. So if I do this, actually it should work. Yeah, okay. OCaml is waiting for us to type something. 1 plus 2. So 1 plus 2. And it says int 3. OCaml is telling us the result of the calculation. To leave OCaml, give the exit 0 command, again ending with 2 semicolons to tell OCaml we have finished typing. Exit O. You should find yourself back where you were before. If you make a mistake when typing, you can press Control C. And tap the C key. This will allow you to start again. Really? 1 plus 3. Oh, it does actually. Okay. We are ready to begin. Nice. So that was actually getting ready. Yes, that was getting ready. It would be nice if we, okay, the book, like if it had here that you can just go to the next chapter, but okay. Starting off. Now, we will cover a fair amount of material in this chapter and its questions, since we will need a solid base on which to build. You should read this with a computer running OCaml in front of you. Consider first the mathematical expression 1 plus 2 times 3. What is the result? How did you work it out? We might show the process like this. Now, is this maybe without the dark mode? Oh, because this is canned or something. So 1 plus 2 times 3, 1 plus 6, and 7. Yeah, now he's talking about order, I guess, of evaluation. How did we know to multiply 2 by 3 first? Instead of adding 1 and 2. How did we know when to stop? Let us underline the part of the expression which is dealt with at each step. So yeah, we first do 2 times 3, and then we do 1 plus 6. I forgot the names of these rules. Why do we first do multiplication and then, yeah, why do we first do multiplication and then addition? PEDMAS, yes. Parentheses, exponents, multiplication and division from left to right, addition and subtraction from left to right. You should log in. Okay. So 1 plus, and then we first do this, and then this, and then this. We chose first part of the expression to deal with each time using a familiar mathematical rule. Multiplication is done before addition. Yes, that's the rule. So we stopped when the expression could not be processed any further. Now, I guess everyone can relate to this. That's how much math we do know, right? OCaml will not actually show this. You know, if you do 1 plus, what's the 1 plus 2 times 3? 2 times 3, and you have to use a star. Oh, it will just show the result. It won't show the steps though. But I guess that's the same, right? I don't know if you could do 2 times 3. Can you do this? 1 plus 2 times 3. True. Okay. I've used the two equality signs to test for the equality. So it's almost like saying is true equal to true. And you will say true because, yeah, so the double equality sign, now I'm going into bowls, sorry about that. But the double equality sign is like the test is something true. And the one sign, true, true, it won't work because, or it will work. No, it's like you use like let name is, I don't know if this is correct. Let name is Domagoy, you know, syntax error. It's not the way you write this. Yeah, let name is Domagoy, like this. Yeah, string. So you bind. Well, now I'm going to variables. I shouldn't go so fast. All right, we chose which part of the expression to deal with each time using a familiar mathematical rule. Multiplication is done before addition. We stopped when the expression could not be processed any further. Maybe let's turn on the dark reader. Computer programs in OCaml are just like these expressions. In order to give you an answer, the computer needs to know the rules you know about. The computer needs to know the rules you know about how to process the expression correctly. In fact, 1 plus 2 times 3 is a valid OCaml expression as well as a valid mathematical one, but we must write star instead of X, since there is no X key on the keyboard. OCaml. 1 plus 2 times 3 and 7 here. A hash or yeah is OCaml prompting us to write an expression, and 1 plus 2 times 3 semicolon twice now is what we typed. The semicolons followed by the enter key tell OCaml we have finished our expression. OCaml responds with the answer 7. OCaml also prints int, which tells us that the answer is a whole number or integer. Let us look at our example expression some more. There are two operators, plus and x. There are three operands, 1, 2, and 3. So yeah, that's the difference, right? You have the operators and they are working on operands. When we wrote it down and when we typed it into OCaml, we put spaces between the operators and operands for readability. How does OCaml process it? Firstly, the text we wrote must be split up into its basic parts, 1 plus 2 times and 3. OCaml then looks at the order and kind of the operators and operands and decides how to parenthesize the expression, 1 plus 2 times 3. Now, processing the expression just requires dealing with each parenthesized section, starting with the innermost and stopping when there are no parentheses left. Let's switch to light mode again. One plus 2 times 3, 1 plus 6, and 7. Okay, well, that's kind of the same thing as before. OCaml knows that x is to be done before plus and parenthesizes the expression appropriately. We say the x operator has higher precedence than the plus operator. Yeah, so we say because multiplication is done before the addition, so the multiplication has a higher precedence than the plus operator. Higher precedence is something that is done before. Yeah. I guess for someone, I guess you need, it's interesting the way we use these words. Before is interesting, yeah. So something that is higher, it's also before. Isn't that kind of weird, right? I mean, it's not weird, but it's just the way we mentally think about these things, I guess. Mentally think about it. Operator has higher precedence. Okay. An expression is any valid OCaml program. So an expression can be anything, right? Anything what you type here is an expression, right? Even 1, it's an expression or just a name. To produce an answer, OCaml evaluates the expression, yielding a special kind of expression, a value. In our previous example, 1 plus 2 times 3, 1 plus 6, and 7 were all expressions, but only 7 was a value. So that's the main, actually, difference what he's talking about. You could say that these are all values, but I guess, yeah, it's interesting. So it's like the last one is a value. Or you could say 1 plus 2 times 3 is an expression that can be reduced, right? So that can be reduced into 1 plus 6. And 1 plus 6 can be reduced to 7. And kind of a mind-blowing I don't know. It took me. It was actually fairly, recent. I was looking at, like, when you say 1 plus 6 is 7, you're not actually adding two values. You are reducing an expression of 1 plus 6 into a value which is 7. It's kind of weird, actually. Right? I don't know. I don't know if that makes sense just by saying it, because it's like these words I know from before, but sometimes only after a lot of time you understand them in a different way or in the same way, but it's like there is more light. There's more light. I mean, 1 plus 6. I don't know. I guess we are used to, I have a 1, I have a 6, right? And it's like if I add 1 and 6, I may even destroy 1 and 6. And because I will get 7, what happens with the 1 and the 6? What happened with them? Were they in some places? Was there 1 there and 6 there, and they came here? We combine them when we have 7. That almost sounds like imperative style of programming. But what's interesting is you're actually not, you're combining, yes, but these are expressions. An expression, it's 1 plus it. Maybe chat will, it is something, something very interesting. So recently, I understood, let's say 1 plus 6. 1 plus 6 equals 7. In functional programming, it's not about adding two values that are, let's say, to use a metaphor / analogy, 1 from there and 6 from there, and we add them, and what happened to them now when we have 7. But in functional programming, we are reducing the expression of 1 plus 6 into 7. So it's like we didn't destroy anything, destrogy. We didn't destroy the two values. We reduced them. We simplified them. And they mean the same. Do you see what I mean? I absolutely see what you mean. And this realization is a profound one when it comes to understanding functional programming and its emphasis on equational reasoning. In functional programming, expressions are immutable and exist as abstract representations that can be evaluated or reduced to simpler forms. When you write 1 plus 6, you're not thinking of destroying the numbers 1 and 6 to produce 7. Instead, you're expressing a relationship, a computation or a transformation that happens without losing the integrity of the original values. That's what I wanted to say. To break this down, immutability. So the values 1 and 6 are not changed. They exist as they are, unaffected by the computation. Instead of thinking of them as used up, think of them as components of a broader computation, reduction. In functional programming, 1 plus 6 is an expression that reduces to 7. The key insight is that this reduction is a transformation, not a mutation. It's like saying this whole thing, 1 plus 6, can be seen more simply as 7. Equivalence. The meaning of 1 plus 6 and 7 is the same in the context of the program. They are interchangeable. You see also this, like it's interchangeable. You never think that. We think in time. I have 1 plus 6 and now that's 7. But I guess you never think it's interchangeable. Well, it is interchangeable actually if you look at it through math, right? If you have 1 plus 6 on one side and 7 and then they can change sides. Because of the concept of referential transparency, you can replace any expression with its evaluated result without changing the program's behavior. Now, this is interesting and it's kind of weird because I would almost say that on a deeper level, 1 plus 6, why wouldn't this change program's behavior in some sense? Maybe the result will be the same, the reduced value, but there are so many ways in which we can do computations, right? Have you thought about that? It's like well, even this example, right? So we have 2 plus 3 times, let's say 2 plus 3 times 4. And that's 14. But we can do 2, yeah, we can do 2 plus, no, we cannot do, yeah, because we have 2 plus 12. Yes, but there is another example. Let's say we have 2 times 3 plus 3 plus 4. And that's 10. So there, we could do it also 2 times 3, right? Plus, no, wait a second, 2 times 3, plus 4. What am I trying to do? Yeah, I failed. I was trying, sometimes you can multiply the two numbers and add them, or you can just, you have 2 or 3 ways how you could solve something. But it has more steps, like one way will have more steps. I'm trying to think of this, wait. This is different from, okay, let's get back to this. This is different from how we often think about operations imperatively, where we might imagine values being used up or combined in a way that implies change or destruction. Functional programming encourages you to think of computations as transformations of expressions, rather than actions or processes that modify state. Yeah. So I was thinking of, but it doesn't. Okay. Yes, 1 plus 6 is kind of the same, or can be exchanged with 7. But what about different ways you can evaluate an expression? Because some ways could take more steps than others, even though both could evaluate to the same result. You're diving into the fascinating world of evaluation strategies. Yes, the process of reducing an expression can differ even though the result remains the same due to referential transparency. Eager evaluation. The arguments of a function are fully evaluated before the function is applied. Okay, that's call by value actually. Add x, y, x plus y, add 1 plus 2, 3 plus 4. Here 1 plus 2 and 3 plus 4 are computed first to give 3 and 7. And then 3, 7 is evaluated to 10. Oh, this approach can sometimes perform unnecessary work, especially if not all arguments are needed. Lazy evaluation. Non-strict evaluation delays computation until the result is actually required. Yes, when we do this, add doesn't immediately evaluate its arguments if only x is needed. Y might never be computed at all. For instance, in add 0 infinite loop, since x is already 0 and addition with 0 doesn't depend on y, the second argument infinite loop is never evaluated. Normal order against applicative. Yeah, also, this is how we do it in our heads, I guess. This sounds kind of, mathy and also complicated. But this is how we do math in school, right? So always expand the expression as much as possible before performing any reductions. So 1 plus 2 plus 3 plus 4, and now 3 plus 3 plus 4. 3 plus 7, 10. So you see, and you do it, and you don't do it at the same time. Sometimes we do it at the same time in our head, right? You see 1 plus 2, 3, 3 plus 7. Like you would skip this part. We don't do this in our heads, like 3 plus 3 plus 4, 3 plus 7. We don't do, yeah. I mean, I don't think most people do it like that. Applicative. Fully evaluate arguments before applying the function. 1 plus 2 plus 3 plus 4, 3 plus 7. Yeah, this is interesting. I guess we kind of do it like this. All right, I'll get back to the book now. Each expression, and so each value, has a type. The type of 7 is int. It is an integer. The types of the expressions 1 plus 6 and 1 plus 2 times 3 are also int, since they will evaluate to a value of type int. The type of any expression may be worked out by considering the types of its sub-expressions and how they are combined to form the expression. For example, 1 plus 6 has type int because 1 is an int and 6 is an int, and the plus operator takes two integers and gives another one their sum. So because, yes, it's almost like, if you, well, it's almost like has to do with like child and a parent, right? So if you have one that is a number, if you have like, and I have like a number plus a number will give a number. And in the same sense, if this type plus that type will give, well, this type and this type, because it has to be the same type. You cannot add actually different types because that would make no sense, right? It's almost like you cannot add a name and a number, right? You cannot say my name plus 4. That wouldn't be the same type. So here are the mathematical operators on integers. Let me just check how is, yeah, it's 49, okay. So we have addition, subtraction, multiplication, divide A and B, and mod. So you can do 2 plus 2, 2 minus 2, 2 2 times 2, 2 divided by 2, and 2 mod 2. This 2 mod 2 is very complicated. It's not, actually, I think, but for me it is. It never made sense, although it does make sense. But it does make sense. Let's do 14 mod 12. It's 2. That makes sense. So 14 mod 12, it's almost like how much is 14 hours, right? And mod 12 is because then it has, okay, a day has a day. We can say 14, but it has 12, right? What do you call it? A clock or what, right? A clock has it goes from 1 to 12, right? And then of course you can go 13 and 14, but it still goes, it goes like twice then in a round. So that's actually mod 12. So if I say how much is 14 mod 12, that's 2. Then it makes sense. So if we say 16 mod 12, we'll get 4 o'clock, because 16, right? 1600 is 4 o'clock, and that's int is 4. So when we say 10 mod 12, it's 10, right? Does that make sense? So the mod and divide operators have higher precedence than plus and minus. For any operator above, this is used here. It's not said what is it, but I think this is the mathematical symbol for an operator. But I think this is a general kind of symbol for, yeah, in math terms. So is this a general kind of symbol for an operator? Yes, the symbol, this plus sign, is a general purpose mathematical operator often referred to as circle plus. It doesn't have a fixed meaning by itself, but is used in various contexts to represent different operations. So I guess that implies all the operations that we can use, maybe on this level, as in plus, you know, minus, divided. Because you see this here is used to some like vector spaces. In logic is used to A and B is true if A or B is true but not both. Often denotes the exclusive OR operation. Oh, A or B is true if A or B is true but not both. Exclusive, so this or this. Okay, we don't use this actually in real life. That's exclusive OR. It's called exclusive because like this entire statement is true, but only if one of these is true. We usually in real life mean, okay, I'm going to do this or this, and both is true. So you just pick, you know, this or this. But here it's used like this or this, but not both. So one of them is not true. So it's like I'm lying or I'm saying the truth. That would be an exclusive OR. I guess if I say I'm lying or telling the truth would be a proper exclusive OR. The testament, I'm lying or telling the truth, is indeed an XOR, because only one of the possibilities can be true at the time, but not both. If you're telling the truth, then the claim I'm lying must be false. If you're lying, then the claim I'm telling the truth must be false. Thus, the truth value of one excludes the truth value of other, which is the essence of an exclusive OR. Do you see what I mean or not? Am I lying or telling the truth? Okay. We sometimes write down the type of an expression. Wait, for any operator above, the expression A operator B operator C is equivalent to A operator B in parentheses operator C rather than A operator B operator C in parentheses. We say the operators are left associative. Yeah, I kind of get this, but I think I read many times of this, about this. I'm not sure how. We sometimes write down the type of an expression after a colon when working on a paper to keep it in mind. So I guess you can check that. Maybe that's not so clear, you know. The grouping starts from the left. Evaluation proceeds left to right. So many operators in mathematics or programming are left associative. Bitwise, consistency. Yeah, okay, well. Negative numbers are written with a minus before them. Okay, so I thought like you don't have to put them inside of a parentheses. Minus 10. What if I just do this? Yeah, it won't work. I have to, so you have to add space though. And if I do like this, let's see. So if I do like this, like this, yeah, now it works. So you do have to put space, or simply put it in parentheses. Sometimes instead of numbers, we would like to talk about truth. So now he's going into booleans. So first, what was introduced so far? Just numbers. So we've been basically using OCaml as a simple calculator. And also we learned that the numbers have a type of an int. So now we're going to change. Sometimes instead of numbers, we would like to talk about truth. Either something is true or it is not. For this, we use the type bool, which represents Boolean values, named after the English mathematician George Boole, who pioneered their use. There are just two things of type bool, true and false. How can we use this? One way is to use one of the comparison operators which are used for comparing values to one another. For example, OCaml. 99 is larger or greater than 100, right? So you say 99. Maybe I can even put this bigger like this. Yeah. 99 like this. Yeah, nice. 99 is larger than 100. Bool false. So and 100 is larger than 99. Bool true. here are the comparison operators. Okay, so we have true if A and B are equal operator. Oh, so we don't have to put two signs. I thought we have to do two equality signs. A equals B. So we could do 100 larger or greater than 99 is the same as, okay, that's false, right? Or true? That's true, actually. 100 and greater than 99 is the same as 99 greater than 100. Is that true? No, that's not the same. This evaluates to true and this to false, and true equals false will give false. So we should get false. Has type int, but an expression was expected of a type bool. Oh, interesting. Can I do it here now? 100 greater than 99, like this. 99 greater than 100? No, I cannot do this. I see, I just wanted to compare the two values. Because if I do this, greater than 99, it says true. But how can I compare? You see what I want to do? I just want to compare this true with another, comparison, and compare true and true. True if A is less than B, true if A is less than or equal to B, A greater than B, A greater than or equal to B. True if A is not equal to B. Not equal, so I guess it will be like this, 1 and 2. This will be true, so 1 is not the same as 2. Okay. Notice that if we try to use operators with types for which they are not intended, OCaml will not accept the program at all, showing us where our mistake is by underlining it. 1 plus true. Okay, we cannot add a true, like 1 to true. This expression has type bool, but an expression was expected of type int. You can find more information about error messages in OCaml in the appendix Coping with Errors at the back of this book. There are two operators for combining Boolean values, for instance, those resulting from using the comparison operators. For combining Boolean values. Okay, the expression of A and B evaluates to true only if expressions A and B both evaluate to true. The expression A or B evaluates to true only if A evaluates to true, B evaluates to true, or both do. So this or is not exclusive. The AND operator, pronounced AND, is of higher precedence than the OR operator, pronounced OR. So A and B or C is the same as A and B or C. A third type we shall be using is char. Okay, now he's going into char. But now we can actually do what I wanted to do before. So 100 greater than a 99. That's true, right? And so we use this, and 99 greater than 100. It's false. So the result of this expression will be false. And it's a false. Right? But if we do 100 greater than a 99 or 99 greater than 100, now it will be true because one of these is true. If it was exclusive OR, it will be false because one of them is false. Yeah. Okay. A third type we shall be using is a char, which holds a single character, such as a or a question mark. We write these in single quotation marks. Okay. So we have like a C. Char. Like this, char. So I guess this would be a string. This would be a string, okay. So far we have looked only at operators like plus, mod, and equal, which look like familiar mathematical ones, but many constructs in programming languages look a little different. For example, to choose a course of evaluation based on some test. Now we're coming to the conditionals. We use the if, then, else construct. OCaml. So if 100 greater than 99, okay. If 100 greater than 99, then 0, else 1. So if 100 greater than 99, this is true. Then true. Then this, right? If this is true, then do this. So if this is true, then do that. If it's not true, then do this. Right? It's something actually what's kind of clear. If 100 greater than 99 is true, then 0, else 1. So we're going to get then 0. Will it work if I put a char? If 100 greater than 99, then true, else false. String true. So you could say if 2 plus 2 is, if 2 plus 2 is 4, right, that's nice. So look at this, if 2 plus 2 is 4, then true, else false, and string true. But I think you don't have to put is 4. OCaml, will OCaml, no, because if we do 2 plus 2, look at this, 2 plus 2, then true, else false. This expression has type int, but an expression was expected of type bool because it is in the condition of an if statement. So you could say if 2 plus 2 is 5, let's say you say 2 plus 2 is 5. Someone says to you, how much is 2 plus 2? And you say it's 5. Well, then you say if 2 plus 2 is 5, then true. Else, otherwise it's false. And that's false. Yeah, okay. The expression between if and then, in our example, 100 greater than 99 must have type bool. It evaluates to either true or false. Yes, the reason why this didn't work, because 2 plus 2 would evaluate to an int. And that's why, yes, it wrote the expression has type int, but an expression was expected of type bool. And while when we say 2 plus 2 is 5, although these are numbers, 2 plus 2 is 5 is false. 2 plus, you could say 2 plus 2 is not 5, but it's not how it works. Like 2 plus 2 is 5 is false. Yeah, I guess you always have to be positive, right? Like you don't say 2 plus 2 is not 5. You say if 2 plus 2 is 5, then that's false. Right? Like sometimes we don't talk like that. You say 2 plus 2 is not 5. That's not 5. You say, well, if 2 plus 2 is 5, then that's false. We don't talk like that. But it does make sense, because if 2 plus 2 is 5, you somehow confirm what's said, or you repeat what's said, and then you say some kind of a value statement about that expression. You don't say it's not valid. You say, if that's valid, then that's false, right? Or you could say to someone, yeah, if what you're saying, sometimes we say it like, well, if what you're saying is true, then, I'm false, or then whatever happened, and then you try to describe so that the person sees that it's not true. But you say like, well, if that's true, then I'm, yeah. It's interesting when you think of this, how we use these terms in, daily life. The whole expression evaluates to the same type int, because either then part or the else part is chosen to be the result of evaluating the whole expression. And we have here, if 100 greater than 99 is a bool, then int, else int. So everything is an int. But I did try to, I did change the type, in the sense that if this is true, then type true. We have covered a lot in this chapter, but we need all these basic tools before we can write interesting programs. Make sure you work through the questions on paper, on the computer, or both before moving on. Hints and answers are at the back of the book. What are the types of the following expressions, and what do they evaluate to, and why? Well, the type of 17 is an int, right? So if we press 17, we get an int. So the type, what are the types, and what do they evaluate to, and why? What do you mean, why 17 an int? Not sure. 1 plus 2 times 3 plus 4. So 1 plus 2 times 3 is 6. 1 plus 6 plus 4. 1 plus 6 plus 4 is 10. 1 plus 10 is 11. So if you write 1 plus 2 times 3 plus 4, it's 11. It's an int. 800 divided by 80 divided by 8. That's an int also. Is it an int? Divided by 80 divided by 8. Well, an integer is a whole number. It is? It is. Oh. $800 divided by 80 divided by 8 is 1. Oh, it's 1. Is it 1? No, wait a second. Is it 1? $80 divided by 8 is 10, and 800 divided by 10 is 800. Why am I confused by this? 800. It's weird. Oh yes, because it's not 1. So it's 1.25. Oh, so it does only show an int. Even though it's not an int, the result is actually a floating point number. Floating point, or like decimal point. It's 1.2, so it's a decimal number, or like a real number, right? It's not an int. So an int is a whole number. So I'm not Sure, how would you get this? How how would you get this type in OCaml? How would I get this type? How would I get the proper type? Because when I divide this in OCaml, I get the int and 1 as a result. Yes, so that's the integer division. OCaml performs integer division when both operands are integers. So that's why integer division truncates the result to the nearest integer towards 0. So because it's 1.25, the result is 1. 10, yes. So let's do it like 10 divided by 8. We get int 1. I see. Floating point. To perform division that results in a floating point number, you must use the divide dot. Oh. I see. So what we do, 880.8. Did you mean 800? This expression has type int, but an expression was expected of type float. Because, oh, that's interesting. Ah, but it expects the input to be float. AT dot. That's a lot of dots. So you mean I have to do 800 dot dash slash dot 80 dot slash dot 8 dot slash dot. Syntax error. Interesting. Yeah, I'm not sure. Maybe I could put the dot only on the first number. Actually, 800 dot and slash dot 80 slash dot 8. Did you mean 80? Or all of them have to be dots? 800 dot slash dot 80 dot slash dot 8 dot semicolon semicolon. Oh, it's complicated. Float. Okay, well, that was kind of complicatish. So we have 400 greater than 200. That will be a bool, right? And then we have 1 is not the same as 1, which is false. Bool false. And then we have true or false, which will be false. No, it's true. True or false is true. Yeah. And true and false. Oh, true and false will be true, will be false. Because if true and false, they give false. Okay. If true, then false, else true. This will be false. So if true, then true. If true is true, then false, else true. This is kind of a trick statement, because if something is true, then false, else true. But Oh, interesting. So it's like if, yeah, it seems to be that like this thing, the then part is not connected in such a way to this part, because if true, then false. So if something is true, if 2 plus 2 is 4, if that's true, if some expression is true, then false. Okay, make a pause now. Yeah, it sounds like a trick. It's like a trick question. The percentage sign. What's the percentage sign? Is this recording? It's not recording. Desktop audio. Why is this not recording? Oh. Hello. Desktop audio. Oh, it's recording. I just have 2 desktop audios. It's recording. Okay. Yeah, so the percentage sign it's a character, yeah. So A plus B. But we cannot add 2 characters, right? That would be, I mean, we could add them, but the proper meaning of the word to add it would be to concatenate. Yeah, I'm not sure how that's used in OCaml. So let's say we have an A and we add a B to it. So, yes, this expression has type char, but an expression was expected of type int. So I don't know if that's the proper way, like this plus plus, right? Unbound value, yes. It's not the way. I think that's how you add chars in Haskell. Consider the evaluations of the expressions 1 plus 2 mod 3, 1 plus 2 mod 3, and 1 plus 2 mod 3. What can you conclude about the plus and the mod operators? 1 plus 2 mod 3. Int is 3. Yeah, mod has higher precedence. So we're basically saying mod plus 2 mod 3. I guess a good way to think about mods is a clock. But instead of just, if it's mod 3, you imagine, okay, I think this is actually helpful for me at the moment. If I see mod 3, I will imagine a clock that has 3 hours, almost as if we are living on a planet where, let's say, a day lasts, wait, I'll try it like this. Yeah. Okay, so two mod 3. So I'm 10 mod 12 is something that we can relate to, right? So it's 10 o'clock and mod 12 is the clock, right? And because we live on a planet where a day lasts for 12 hours. Well, a day and a night, they last for 24. So this is like we live in a planet where a day and night lasts for 6 hours. So then the clock itself will have 3. And then it will go around again 3 when it's, like midnight. Midnight would be a 3. And then one more 3 until the next day. Midday, right? So 2 mod 3 is 2, right? 2 mod 3 actually is 2, int 2. And 1 plus 2 mod 3 is 3. Okay. So what is he basically asking? 1 plus 2 mod 3. Oh, what can you conclude about the plus and mod operators? Yeah, so 1 plus 2 mod 3 is 3 mod 3. 3 mod 3, that's 1. 3 mod 3, that's 1. I'm sorry, my cat is trying to scratch something, and the family is asleep, so I'm trying to, okay. 1 plus 2 is 3, and 3 mod 3. So we'll get basically 3 mod 3, which is 0. Right, because it's the same. Is she trying to get out? Czy się ćma? Chodź. Czy się ćma? Okay. She wanted to go out, okay. And 1 plus 2 mod 3. So 2 mod 3 again is 2, and 1 plus 2 is 3. So what can you conclude about the plus and mod operators? Well, mod has a precedence, so I guess you don't have to put 1 plus and in parentheses 2 mod 3. A programmer writes 1 plus 2 times 3 plus 4. What does this evaluate to? What advice would you give him? Oh, I would probably give him an advice. Well, depends what he wants to do, but I guess the way it's written here is 1 plus 2. Wait, you know what's good? I like this GNOME extension. It's zoom. What is this? Magnify. No, zoom. Better desktop zoom. What is this called? Cursor. Cursor zoom. Pointers area action, eye on cursor. Wait. Magnifies the cursor. Yeah, wait a second. I'll try to find this. It's fun. Wait. I'm recording again. Yeah, I just installed the Zoom thing. It's kind of nice. So Zoom has this better desktop zoom. And let's go to options. Use scroll gesture to zoom desktop. Yes. Modifier keys for scroll gesture. Super Control C. Super Control C. All right. Now if I do like this, you see this? This is nice, so I can zoom here. All right, this is cool. So that means if I do like this. All right, why was it doing this? Did this thing install fail to build? Invalid command. Yeah, I was trying to install MyPaint. Not sure why this thing didn't install. MyPaint. Oh, it didn't work. Look at this. Horrible. Nix, what happened? You see, this is the problem sometimes with Nix. Things don't work. Invalid dash separated option. Underscored install script instead. This depreciation is overdue. Yeah, I don't have my paint now. I wanted to use my paint to make some drawings later in this. Invalid command test. Yeah, maybe I should check the my paint Nix sauce. Build failure. Yeah, now I'm doing something else, right? My paint, yes. Additional. Was this recently? October 15th. This is an instance so far. I have not managed to port it to PyTest, so we need to disable tests for now. Oh, interesting. Build failure. This would be interesting to kind of explore for Nix sauce. This is open still. Wow, okay. I could maybe try it, and I could maybe try something with this. I'll keep this tab open. Okay. So what advice would you give him? So 1 plus 2 times 3 plus 4. Well, the advice would be to have 1 plus 2 in. So the advice would be to put a lower precedence operator in parentheses, so that the higher precedence one, like the multiplication, will not, so to say, take the operands. This is so badly explained. But yeah, you should put this in parentheses so that you can add this first if you want that, right? Otherwise, you do 1 plus 2 times 3 is 6, plus 4 is 10, and this plus 1 is 11, right? Okay, the range of numbers available is limited. There are 2 special numbers, min-int, and max-int. What are their values on your computer? What happens when you evaluate the expressions max-int plus 1 and min-int minus 1? Interesting. Does this work really? So we have min-int. Oh, so it does print the minimal int. I think they depend on the, amount of memory or something like that. And max-int. Yeah. So what do you mean if we do max-int plus 1? Max-int plus 1. It goes... Wow. It's like mod. So when we do the maximum number and we add 1 to it, it's almost like adding... just it starts again from the minimum number, right? Because if we do now max-int plus 2, look, from 4 it changed to 3, so it's going again. Fascinating. So I guess max-int plus max-int will get you to -2. Yeah, I thought it would be like 0, but it's actually -2. So max-int then minus min-int will get you -1. Okay. What happens when you try to evaluate the expression 1 divided by 0? Why? So 1 divided by 0, exception, division by 0. Right, we cannot divide that. Why? Can you discover what the mod operator does when one or both of the operands are negative? What about if the first operand is 0? What if the second is 0? Okay, so it makes sense with that clock thing. But now it gets a little bit more complicated with both of the operands are negative. So how do we, so now it's hard to compare that, right? Like you don't say it's minus 10 o'clock. But you do think in also negative terms. When let's say now is 2 o'clock and someone tells you we were supposed to meet at 10. Like if you go if it's now 14 and you go 4 hours in the past, so it would be like 14 minus 4. It's 10. No, but you could say 2 minus 4 is 10, right? Which is false. But if 2 o'clock, 2 p.m., right? Minus 4 is 10. But here it says, when one or both the operands are negative. So let's do our again, 10 mod 12. It's 10. Minus 10 mod 12 is minus 10. 10 mod minus 12 is 10. Minus 10 mod minus 12. It's minus 10. If it's 0, 0 mod 12 is 0. 10 mod 0, well, that should be 0. Because you did division by 0. Okay. Why not just use, for example, the integer 0 to represent false and the integer 1 for true? Why have a separate bool type at all? Because it's good to have a type for a bool. Otherwise, it's like fake. That's not really a good explanation, right? I know in some other languages you don't have bool implemented as a type. I think in C or like some other imperative languages, or maybe Python, like bool itself is just, like 1, and false is just defined as 0. And that's a bool, right? But this is a good question, which I'm not sure what to say, but maybe chat will know something. Let's do this. The decision to have a separate bool type rather than just using integers reflects both design principles and practical considerations. Here's why: a dedicated Boolean type exists and is preferred in most programming languages. Boolean. I like, because I heard some functional programmers, I think Graham Hutton says Boolean, while some say, Boolean. I kind of like both. I guess depends on the situation. It depends on the type. Clarity and intent. Using a dedicated bool type explicitly communicates the intent of the code. When a variable or expression is of type bool, it clearly represents a logical value, true, false, rather than a numeric value. Yes, but you could define it, right? Type safety with bool logical operations. Yeah, but what about the point that I heard that in Python or C, the Boolean is basically defined as 1 or 0 in the library, which is not the case with Haskell and OCaml. Okay. In languages like Python and C, the Boolean type is closely tied to integers, often being represented internally as 1 and false, as 1 is true and 0 is false. On the other hand, languages like Haskell and OCaml treat Booleans as an entirely separate and distinct type without a direct numeric interpretation. Yeah, why is that? You kind of get it, but in C, historically, there wasn't a separate bool type. Yes, I was doing that in C. Like, you don't have a bool type. You have to include it as a header, standard bool.h. Logical values were represented as integers. 0 means false, and a non-zero integer means true. The bool type in C99 is essentially an alias for an integer with false defined as 0 and true defined as 1, right? Bool flag is true. Internally, this is just an int with the value 1. Python is the same, right? While Python has a distinct bool type, it's implemented as a subclass of int. Why is that true? Designed with minimal abstraction and representing true and false as 0 and 1 was both simple and efficient for hardware and low-level operations. Now, in Haskell and OCaml, Booleans are treated as distinct algebraic data types. They have no direct connection to numbers. Bool is a distinct type with 2 possible values, true and false. It cannot be used interchangeably with numbers unless explicitly converted. True plus true. I guess you could do that in Python, true plus true. Oh, that's horrible. Wait, in OCaml, the bool type is a separate from numbers. There is no automatic conversion between bool and int. Okay. What is the effect of the comparison operators like less than and greater than on alphabetic values of type char? For example, what does p less than q evaluate to? Oh, I haven't tried that. So p, a char p, less than q. It's true. Well, I think it's kind of the alphabetical order, right? No? What is the effect of the comparison operators on the Booleans, true and false? What is the effect of the comparison operators on Booleans? What is the effect? I don't understand the last question. I really don't. I don't understand the last question. The question is about the behavior of comparison operators less than and greater than when applied to 2 characters of type char or 2 Booleans, true and false. Let's break it down for clarity. Characters are often stored internally as their numeric codes, typically using ASCII or Unicode encoding. When you compare two characters with less than or greater than, the comparison is done based on their numeric values. So example, p less than q in ASCII or Unicode, p has a numeric a value of 112 and q has a numeric value of 113. So when you compare p less than q, you're asking, is the numeric value of p less than the numeric value of q? Right, they're saved as numbers. So alphabetic ordering of characters corresponds to their numeric codes. Okay. Is that it? That's it. Starting off, back to contents. All right, this took a while. Names and functions. Hour and 46. Names and functions. So far we have built only tiny toy programs. To build bigger ones, we need to be able to name things so as to refer to them later. All right. We also need to write expressions whose result depends upon one or more other things. Before, if we wish to use a sub-expression twice or more in a single expression, we had to type it multiple times. Okay, he's using this example. Let's say you have to write this 3 times. Right, and instead we can define our own name to stand for the result of evaluating an expression. To stand for the result, and then use the name as we please. So right, so what he's saying, instead of saying, 2 plus 2 plus 2, right, in 6, you could say let x equals 2. Is it like that? Let x equals 2. Well, let's not call it. Let's say n. Let n equals 2. So now we have an n, a name for that. And now we can say n times n times n. And we get 8. Or we can do n plus n, and we do 6. Right? So we don't use 2 plus 2 plus 2, 2. It's interesting because when I press and you see these symbols, these are symbols of the arrow keys. I cannot go, I think that's the way this interpreter is coded, but it's kind of weird. When I was trying to build a REPL in C, I'm doing this kind of build your own Lisp. I'm going through that book too. And so one of the first things we did was include a header called, edit line or read line that would somehow interpret these keys and that we can go back and forth in history and such. And I can't do that. Look at this. If I press them, so the computer, actually the interpreter, interprets the arrow keys as these symbols. Why is that? Kind of strange. Okay, I'm back here. I had a pause a bit, and although because I'm just pausing, you don't see it. Yeah, so we are back to learning OCaml. and OCaml from the very beginning. So now we are at, I think we're at let statements. Yeah, right. So let x is 200, val x. So that's a val x is, I think this has a type of an int. That's how you read this. The value x has a type of an int. That's interesting. So when we write what happens when we just press n? So we can call n also, like we don't have to do a calculation of sorts. We can just call n now, and n is 2. But it says n is an int. It does not say n is a value. And here it's interesting. We say let x is 200, val x. Oh, that's only when we defined it, right? So we said let n is 2. So we bind the number to the number value to the variable or a name n. And then the val, I think this means value, right? The value n has a type of int. I think, yeah, in Haskell you use two colons. In OCaml you use 1 colon. Okay. So to write this all in a single expression, we can use the let n construct. All right, I know that from Nix. Let x is 200 in x times x times x. So that's kind of cool. So let x is 200 in x times x, and we get a 40,000. So we could say let x is 2. Let x is 2 in x times x, and then we get a double. Yeah, I think this will be the next step because I just said that already. So it's kind of it's cool, like by combining more and more expressions we will get more and more names. And I guess this is where abstraction comes in, right? It's like how many names can you keep in your head, right? You will need some kind of structure. So will this work in OCaml? Like double is let x. No, well, check, wait a second. Double n is, I'm trying to something. Let n is, yeah, I don't have to say double n. I think I could just name it double. Is let x is 2. Maybe we can call it double and then you keep the word 2, right? Let x is 2 in x times x, or x plus x. I think is the same. Although I'm sure probably it's way different than how is this. I'm actually wondering now, is there any difference how this is represented in the memory? X plus x or x times x? Like what's faster? Unbound value double. Maybe I need to have also let with double. I know this would work in Haskell. Is it let double equals let x is 2 in x times x. Let double int is 4. So can I call double now on like on 4? This expression has type in. This is not a function. It cannot be applied. Oh, I cannot do this. So even double, yeah, I don't know how to do this. I would know how to do this in Haskell or in Nix, not in OCaml. All right. Let x is 200 in x times x times x, and let a is 500 in, we have here some kind of a sub-expression. My recording, I am. we have here a sub expression. Let A is 500 in, but we're just using this to call this A, I guess you could say from the outer scope. And this is a inner scope. Let B is A times A in A plus B. This is a nice way to put this. Let A is 500. Okay, A is 500 in what? In let B is A times A. So we have A is defined as 500. In what? I guess we're gonna call that. And we are basically going to square A times A, and we're going to put that inside of B. We're going to bind that, the result of A times A, to B. So let B is A times A. Let B is A times A in A plus B. This is interesting. So let A is 500 in let B is A times A in A plus B. It's kind of an interesting, on the first look it might seem confusing, but so let B is A times A. I'd like to use something. Oh, I can't use these things. That's weird. Let A is, let's do 2. And let B is A times A in A plus B. So what is this going to be? So A is 2, right? It's almost like the A is almost, so the A is in outer scope. And inside scope, if we go inside, we're going to have a second let. So B is A times A. So A squared, right? So A squared, A is 2. 2 times 2 is 4. So B is 4. Well, B is not 4, actually. No, this is wrong. B is not 4 because we forgot the rest of the expression. Is it? So the value of B is A times A in A plus B. A times A is 4. And 2 plus, oh wow, yeah, this is kind of confusing. There's some recursion going on. This is an interesting example. I'm sure this would be confusing to someone such as myself. But let A is 2 in, and let B is A times A in A plus B. It's recursively calling B because it's funny. You see this? I think it's weird because you call B here, and the entire thing is defined as B. It's kind of interesting. It will be nice, like could you generate a sort of like real life analogy for this recursive call so that it makes more sense? Sure, let's create a real-life analogy for the recursive style evaluation of this expression. Let A is 2 in let B is A times A in A plus B. Real-life analogy. Imagine you're a chef making a recipe. The steps are as follows. Assign a base ingredient. Oh, this is nice. So you decide to use, right, okay. You decide to use 2 cups of flour. So we were making banana bread actually yesterday. We were making, yeah. Let's make banana bread and use 2 cups of flour. We used sorghum, actually, sorghum flour. which is gluten-free and healthy. Okay, let's turn this expression into a banana bread, making an analogy using 2 cups of sorghum flour. Healthy, of course. So the recipe. Translated into banana bread terms, start with the base ingredient A. You have 2 cups of sorghum flour. By the way, it's just a nice flour that we use. Start with the base ingredient. So we have two cups. So that's the base. The A is the base. This is the foundation of your recipe. Let A is 2. Now do an intermediate calculation. So this is an intermediate calculation, B. Oh, interesting. So you decide to make a batter base by mixing the flour with itself. For simplicity, you measure this as the square of the cups of flour. Calculation. B is A times A equals 2 times 2 is 4 cups of batter base. 4 cups of batter base. Let B is A times A. Now you have 4 cups of this rich gluten-free batter. Now combine for the final mixture. I see, but he separated this. I pressed in 6, all right. So he actually separated it. Let B is 2. So 2 times 2 is 4. Let B is 4. In A plus B. Oh, A is outside. Kind of silly now, right? A is 2. It's just we are calling it. I was confused because A was used here. Oh, that's interesting. I was confused because A2 is, I think this was somehow imperative way of thinking for me, because I thought this A2 was kind of lost. I mean, it was used by A times A is 4, and now it was confusing to see A to put 2 into A. I think this may happen, yeah. So A times A is 4 in 2 plus 4, in 2 plus 4, and 4 is actually the result of A times A. So B is A times A. So what does this mean? So this means also, okay, the same thing we can write as let A is 2 and let B is A times A, right? Let's have more space. A times A in A plus, and we could do it like this. Open the parentheses and write, because B is that, A times A, like this. And we should have the same result. Warning, unused var, unused variable B. Yes, we didn't use B, even though we used it just to name a second and intermediate calculation. It's funny. It's like we didn't use it and it's complaining. Oh, I think this would work if we used an anonymous function. Then we wouldn't have to have it named. And I'm not sure how you write anonymous functions in OCaml. But this would solve it actually. Then the compiler wouldn't, or the interpreter wouldn't complain. Right, combine the final mixture. So finally you combine the original 2 cups of flour with the 4 cups of batter to get your total mixture. Yeah, this is kind of confusing, I guess, this analogy, because we presume, I guess, that the 2 cups of flour are gone into the 4 cups of batter, right? You decide to make a batter base by mixing the flour with itself for simplicity, but isn't this confusing? Because in my mind, I presume that the first 2 cups were kind of used for the 4 cups, 4 cups of batter. So why would we combine 2 cups and 4 cups of batter? This is very confusing though. I see where the confusion arises. You're imagining that the 2 cups of flour are used up to create the 4 cups of batter, so it feels strange to combine them again. This interpretation stems from an imperative mindset where ingredients or values are consumed as part of a process. I'm guilty of that. Let me reframe the analogy to better align with functional programming immutable perspective. Key functional concept: immutability. So in functional programming, values are not consumed or used up during computations. Instead, they remain intact, and the computation creates new values. The original 2 cups of flour still exist independently. Let's adjust the banana bread analogy to reflect this immutability more clearly. Start with the base ingredient. You have 2 cups of sorghum flour. This is your starting point, and it remains unchanged. Why would it remain unchanged? Make the batter base. You calculate how much batter you'd get if you combine 2 cups of flour with itself mathematically without using the original flour. This gives you 4 cups of batter. But wait a second, maybe So the recipe says combine the original 2 cups of flour with the 4 cups of batter. Calculate it independently to get 6 cups of total mixture. This is still very weird. The 2 cups of flour remain untouched. Okay. But your egg is kind of confusing because why we wouldn't touch 2 cups of flour? We are making a bread. You're absolutely right. If we're making bread, the 2 cups of flour would naturally be used in the process. Let's reframe this example so it aligns more closely with both the real-world baking process and the principles of functional programming. Imagine this process as more of a thought experiment or plan. The flour represents your starting point. You measure 2 cups of sorghum flour. To figure out your total batter, you think about squaring the amount of flour conceptually, imagining you'd create 4 cups of batter from it. In reality, this batter uses the 4 cups of flour, but the calculation is about how much batter you'd get if you use this amount. Yeah, I guess this, I think this example isn't the best. Do you know some other where nothing is used? This example is really nice, yeah. Where nothing is consumed or used up. A story about counting apples. Let's try this. Start with a base number of apples. You start with 2 apples. These apples are just sitting in basket. Nothing happens to them. Oh, it's like starting to count from 2. Think about grouping the apples. You imagine what would happen if you grouped your apples into 2 baskets, each containing the same number of apples as the total you currently have. Mathematically, B is A times A, 2 times 2 is 4. You don't actually make more apples. This is just a thought experiment about grouping. This is very it's kind of interesting that these examples are very confusing. They're kind of confusing, yeah. It's kind of funny. Yeah, I'll have to think of. It's just weird. Let's try this. Okay, just explain how this code evaluates. Define A, right? So we define A. A is 2 in what? So here A is bound to the value 2. This means that wherever A appears in the rest of the expression, it will be replaced with 2. Okay. You could, that's better. So enter the inner let expression. Let B is A times A in A plus B. Now OCaml evaluates the inner let. B is A times A. Since A is 2, this becomes B is 2 times 2 is 4. So B is now bound to 4. Okay, B is actually bound to 4. I was seeing it wrong. I was looking that B is bound to the entire thing, which is not true. B is bound to the result of A times A. But this in is kind of, I said that because it's in the same line. So I guess you could, yes, you could, I guess you could think that in the wrong way, because B equals and then something in the same line means that the entire line equals B, but it's not true. It stops here in. B is this thing in what? A is 2 from the outside and B is the inner scope is 4 and 2 plus 4 is 6. It's basically very simple. Yeah. How would it look like formatted in more lines? Not all in one, OCaml. I think it would make more sense if we actually let A is 2 in, let B is A times A in A plus B. Yeah, you could say like this. Or we could indent it. Let A is 2 in and we indent this B. I'm not sure if you have to indent in OCaml or what are the indenting rules. That would be interesting. Okay, we can also make a function whose value depends upon some input. We call this input an argument. We will be using the word input later in the book to mean something different. So let cube. So we're going to have let cube is x times x times x. Error unbound value x. Interesting. Let cube x. Oh, I see. It's funny that OCaml, I cannot go in the history. It's really weird. Why? Let cube x is x times x. So cube, so if I do cube 5, it's 125 because it does 5 times 5 times 5. Now it says that val cube int is a function. Okay, the value of cube has a type of int from int to int, has a type of from int to int, and it's a function, right? Not sure the correct way how you would read this. Maybe he will say, we chose cube for the name of the function and x for the name of its argument. When we typed the function in, OCaml replied by telling us that its type is from int to int. This means it is a function which takes an integer as its argument, and when given that argument, evaluates to an integer. To use the function, we just write its name followed by a suitable argument. In our example, we calculated 200 to the third by giving the cube function 200 as its argument. The cube function has type int. From int to int, we gave it an integer 200. And so the result is another integer. Thus, the type of the expression cube 200 is int. Remember that the type of any expression is the type of the thing it will evaluate to. And cube 200 evaluates to 8, blah, blah. An integer in diagram form. From int to int, cube 200. All right, that kind of makes sense. If we try an argument of the wrong type, the program will be rejected. Let cube x is x times x times x, and cube false. The error. The expression has type bool, but an expression was expected of type. So like even if we added cube a, it will say the expression has type char, but an expression was expected of type int. So the expression that it has now and the expression that was expected. I guess that's the way how you would phrase it. Here is a function which determines if an integer is negative, OCaml. Here is a function which determines if an integer is negative. Oh, which determines if an integer is negative. How would we do that? I guess we would use if. Wait, don't look. Let negative is what? Let negative x. You cannot just name it negative. Let negative x is what? If x is less than or equal, no, less than 0, then but what does it want? Here is a function which determines if an integer is negative. Well, okay, then negative, else positive. So if we do neg 1, it says positive. If we said neg -1, -2, this expression has type int string, but an expression was expected of type int. Really? Like this? Now I have to put it in parentheses. Negative. Yeah, this is better to put true and false. Right, so we could have done, this would be actually better. Let neg x is, if x less than 0, then true, else false. So if it's negative, then true, because we are asking if it's negative. That's why we first put true. So if it's less than 0, then true is negative. Otherwise, false. So we do this, syntax error. If really syntax. Else. Isn't it else? It's else. If then else. If x. Oh! Let neg x is if x less than 0, then true, else false. So now neg -1, will it work now? No, it will not. Neg in parentheses -1, true, it's negative. And if we do neg 2, false, it's not negative. All right. We added parentheses to distinguish from neg -30, but of course this is equivalent to just writing let neg x equals x less than 0. Value neg this. Okay, we can do it like that also. We even don't need the conditional, right? If we're going to check the bool. Right, you could do like let neg x equals, well, let neg x equals x minus, what did they do? X minus, really? But this is different. This does not really check. This is just x. This is like saying what is neg x. Neg x is x less than 0, right? That's neg x. So when we do neg 2, it says bool false. Right, it looks like the result is the same, but it's a kind of a different function, right? Before it was checking, now it's not checking. It is checking, I guess, but in a different way. Because x minus 0 will evaluate to the appropriate Boolean value on its own, true if x less than 0 and false otherwise. Here is another function, this time of char bool. It determines if a given character is a vowel or not. It determines if a given character is a vowel or not. This is kind of cool. So now we have a more complicated function, more complex, maybe complicated is not the best word. A more complex function, because before we had a function going from an int to an int, right? Or from a char to a well, only from an int to an int. So first we learned about numbers, basically using OCaml as a calculator. Then we learned about names. So instead of saying some numbers, we put that in a name. So like let n equals 2. And then we did something with n. So it's, well, it's not, I don't know. Could you say that that's, yeah, you could say that's an abstraction, right? It might not be a higher level of abstraction, but it is some kind of, well, because I heard this somewhere used. It is an abstraction, but you could say maybe it's on the same level abstraction, because you're not kind of, well, are you creating a new structure? Maybe. Okay, and now then we used the name and to name a function. So something that applies to that n, right? We applied a negative. Or we made, can we do now the double function? Let negative x is x less than 0. I guess you could say let double x is x times x. And now we have a double function. So you could do double 2 and 4. And you could double 4 and 16. And now, which is a really cool thing, I always wanted to do this. No, you have double and double 4. So now we are calling the double, right? We have two doubles, an outer double and an inner double. So the inner double is going to double 4, you will get an 8. You know what? This is actually wrong. This is squared. This is not double. This only works with 2. It's a mistake. I should let double x equals, because otherwise I'll get 4 times 4, which is 16. That's not double. X plus x. This is the correct double, right? So now when I call double, double 2, double 3. Okay. So I have double 3 is 6 and double 6 is 12. So I should get 12. Right, so this is how we named functions. So some kind of application. But now we have a function going from char to bool. Well, the negative actually, no. So the negative function was a function that was going from int to a bool, because we are giving it an int, but the negative. How do we inspect types? How do you inspect types in OCaml? How do you check the types of a function in OCaml interpreter? utop entering its name. You can explicitly request the type of a function by using the type directive. Show. Val. Really? What do you mean? Like this? Type neg? No. Wait, so show. What do you show? Show add. Show neg. Okay, neg is, yes, neg is a function that has a type from int to bool. And now he's doing char to bool. I guess he's really good doing step by step. This is all very basic stuff. So what is he writing? Let is vowel C. Is vowel, it's all the same. It's vowel C. So it's checking if C. Oh, but it would be nice to store the A instead of checking. Okay, I guess that would be the next step, because is vowel X false? Is vowel C checks with, oh, maybe this was not the best teaching example, because he used C. He used C for char. Okay, I had that's the different way they use in OCaml. I've only used Haskell, and I think for characters they write the X, and for a string X's. But here he's using C, which confused me. I thought like that he's actually checking if C is a vowel, but he's not really checking C. He's defining. So we are defining here a function is vowel, and we are using C just as a placeholder for any character that we will input to is vowel. So is vowel C is. And how is he going to check? Oh, he's going to use OR. He's going to use Boolean operators. C equals A. Can I go to the next line? I can. This is kind of cool. Oh, so I guess you can always go to the next line. And only when you press the double semicolon will the thing stop. So C equals A, or I see C equals E, or C equals E, right? Or C, O, I think O, and U. And that's it, right? And now we put this. And now we have a function is vowel that has a type of from char to bool. So if I do now is vowel A, it will say true. Is vowel X, it's false. Okay. Is a number. I guess you could write the same thing as a number. That would be interesting. So if you like input some kind of a letter, it will say false. And it would, and then if you input a number, it will say true. Notice that we typed the function over 2 lines. This can be done by pressing the enter key in between lines, so OCaml knows that we are finished when we type 2 semicolons, followed by enter as usual. Notice also that we press space a few times so that the second line appeared a little to the right of the first. This is known as indentation and does not affect the meaning of the program at all. It is just for readability. Well, I guess in some programming languages it does affect the meaning of the program, right? The indentation. I guess that's okay to say, because here it does not. But in some, the indentation itself has a meaning, which is kind of cool. Because I guess that means you can, you write less signs, those little, semicolons and stuff, when you can indent code. And maybe it enforces a certain kind of style. There can be more than one argument to a function. For example, here is a function which checks if 2 numbers add up to 10. A function which checks if 2 numbers add up to 10. How would we write that? Let add to 10. I guess we need A and B. If 2 numbers add to 10, so let add to 10, AB. I guess it would check we need a Boolean, right? If they add to 10, well, true, it adds to 10. If it doesn't, it's false. So add to 10, let's say add to 10, we can do this in our heads. Add to 10, 5 and 5. True. Add to 10, 5 and 6. False. So how do we do that? Well, let add to 10 A and B. If A plus B equals 10, then true. Else, false. Is that true? So add to 10, 3 and 7, true. Add to 10, 5 and 5, true. Add to 10, 6 and 120, false. What did he write? Let add to 10 A and B equals A plus B is 10. Right, that's the same thing. So dogite, dođi unutra. Ajde, dođite. Pazi noge. So the type is int bool because the arguments are both integers and the result is Boolean. The type is int bool. Oh, now we have a longer one. This is cool. Okay, now we are going step more. So before we were going from int to bool, the function which checked if the number is negative, right? And then we had a function which checked if a certain, letter is a vowel. So it compared it like with a, e, o, u, right? And that was the function from char to bool. So now add to 10 is a function from int to an int to a bool. Why? Because we have 2 inputs to this function. I wonder if this works. Add to 10, 3, add to 10, 7. This expression has type int to bool, but an expression was expected of type int. This function application is partial. Maybe some arguments are missing. Nice. I like the messages. So I was trying to do partial function application, and that didn't work. Interesting. So the type is int bool because the arguments are both. So let's do our show add to 10. Yeah, this. So add to 10 has a type of int to bool. Okay. So the type is int to bool because the arguments are both integers and the result is a boolean. I like to read it like that now. We use the function in the same way as before, but writing two integers this time, one for each argument the function expects. A recursive function is one which uses itself. Consider calculating the factorial. Okay, now this is a next kind of thing. Consider calculating the factorial. Oh, the factorials. That's so functional. Of a given number. The factorial of 4, written in mathematics, for example, is 4 times 3 times 2 times 1. I guess this is a very good example, but not so many people know factorials. I mean, they know of them, but it's kind of, we never use them. So there is no mental habit. I mean, there is kind of no mental habit of this. You see, there are things that you understand and you kind of use. But I guess if you never use the factorials, you can understand it, but then, yeah. Here is a recursive function to calculate the factorial of a positive number. Note that it uses itself in its own definition. It's funny, like you don't use up, as we said before, the values, but you use the function. So let rec factorial. Oh, we have to add the rec. Interesting. So let rec, I guess recursive. I guess you have to really say it. Factorial A is. And now we have a new line. So let rec factorial A. So what is a factorial, basically? Factorial of a given number. The factorial of 4 is 4 times 3 times 2 times 1. So if we say factorial of 1 is what? A times 1. Yeah, but we cannot just calculate it because factorial of, let's say factorial of A is factorial of 1. Yeah, okay. I'm bad at this actually, at trying to explain this. Okay, factorial of 4 would be 4 times 3 times 2 times 1. So you have to always go up to 1 from that number and multiply. It's like you're doing a countdown, but basically, you know, multiplying these steps. That's an interesting way, I guess, to frame it. It's like a countdown, but you multiply the numbers of the countdown. And that's a factorial. So let rec factorial A. So if we have factorial 4, we would have to do 4 times, yes, how would you do it, right? If you say factorial 4, you can't just write 4 times 4. You have to write 4 times 3 times, how would you do it? You have to do a countdown. But if we say factorial 3, 4 times factorial of 3 is 3 times factorial of 2 is So I guess you have to say a times factorial of what? You can't write a, right? Because if you have factorial, look at this, if you have factorial 4, will this work actually? Factorial a. Let's try to compile this. So look at this. This will probably not work. Factorial 4, factorial 4 is what? Stack overflow during evaluation. Oh, interesting. Looping recursion. Yeah, because we have rec. Okay. So let rec factorial, let rec factorial a is a times, and now we have to say factorial what? Because factorial 4 is 4 times factorial of 3. But how do we express 3? Or any number less than a. So it has to be a number less than the first number, right? If we started with 4, now we need a 3. How do you write 3? You write 3 like a minus 1. Yeah. This should work. So now if we write factorial 4 stack overflow, but wait a second, it's stack overflow. Why? Because a is 4. Okay, a is 4. And factorial 4 minus 1 is 3. So that means we have, right? It will be wrong actually. Let's try to write this, then it will make more sense. So let's say we make factorial let factorial a equals, right? Let rec, I have to use rec, yeah. Let rec factorial a equals a times, right? Factorial a minus 1. This wouldn't work because it's going constantly, right? Wait, I'm gonna tell him, let's say we make, this will result in an overflow. Just show me like in 20 steps what will happen or how the evaluation steps will occur. I just want to show the error in eval steps. So now we'll have, right, now it's going to even go below the 0. It will not stop. We have to like tell it somehow how to stop. Look at this. The function is problematic because it lacks a base case. Factorial 0 is 1, which causes infinite recursion. We have to get to the 0 and stop. And factorial of 0 is 1. Oh, this is interesting. So evaluation steps for factorial 5. So, okay, we start with 5, okay, factorial 5, right? We apply it. 5 times factorial 5 minus 1 is 4, which simplifies to 5 times factorial 4. Now we expand 5 times 4 times factorial 4 minus 1 is 3. So we have now 5 times 4 times 3 times factorial 3 minus 1. That's 2. And 5 times 4 times 3 times factorial 2, which is 2 minus 1 now is 1. So 5 times 4 times 3 times 2 times 1. Factorial 1. Factorial 1 minus 1 is 0. So 5 times 4 times 3 times 2 times 1 times factorial 0. And now 0 minus 1. And then we go to minus 1, and that's the mistake. We should stop at 0. So factorial 0 is 1. So we have to include that somehow in our definition. So it doesn't know how to stop. So we're going to do let rec factorial a is a times. So maybe we need to use an if statement. If factorial 0 is 1. No, that's wrong. Let factorial a is what? Maybe we could use and. Like a times factorial a minus 1, right? That's what we want to do, but we want to stop. And factorial. No. We have to tell it somehow how to stop. A times factorial a minus 1. Like you do that until. It's like we want to make a loop. A times factorial a minus 1. I don't know how to do this. Wow. Right, so the recursion never stops because there's no base case. Maybe if, if factorial a equals 1, factorial of 0 is 1. If factorial of 1, then what? Then stop. How do you say then stop? If factorial a is 1, else keep on doing it, right? Then the recursion never stops because there's no base case. I guess I'm looking at how you do the base case. Factorial minus 1, minus 2, and each step he performs a multiplication. He tries to compute factorial for an even smaller value, resulting in key problems, right? Infinite recursion. The OCaml runtime uses a call stack to keep track of each function call. With infinite recursion, the stack grows indefinitely until the program runs out of memory, causing a stack overflow, fixing the problem. Oh, and we were so close. If factorial, no, if a is 0, if a is 0, if factorial, so if a is 0, then 1. Yes, if factorial a, I was confused by that, right? If a is 0, then just 1. But does that mean it's the end of it? Right, else a times factorial a times factorial a minus 1. This is the correct one. So now when we do factorial 4, we do 24. Really? 4 times 4 is 16. Else a times factorial a minus 1. This is wrong. 4 times 4 is 16. 16 times... No, 4 times 3 is 12, times 2 is 24, times 1 is 24. That's actually correct. Factorial, let's do how integer literal exceeds the range of representable integers of type int. I think it grows like really big, yeah, these numbers. Let's do factorial 100 and 0. Really? 23. Minus. Why minus? $3 million already. Factorial 10. Wow. Would you like a more visual breakdown of the evaluation? Sure. Make something pretty. Here's a visual breakdown of the evaluation steps for your problematic factorial. No, he's doing the wrong thing again. All right. $251. How's the light? Is it too much? All right. So, okay. A is 1. If A is 1, then 1. But what did we write? Really? What did we write, actually? If A is 0, then 1. Because factorial of 0 is 1. And factorial of 1... Oh, this is interesting. Because he used if A is 1, then 1. Else A times factorial A minus 1. We used let rec instead of let to indicate a recursive function. How does the evaluation of factorial 4 proceed? This is nice, yeah. So this is like, it's really, show me the space-time, okay, of the evaluation. I think it's called space-time complexity. Now show me the correct evaluation and the space-time, how do you call it, space-time complexity of the evaluation. How it expands and contracts the recursion. Will it, does it? No. No, just show me in code. Step 6, step 7, collapse and multiply. Yeah, expand. Put all that together. Expand and collapse, so that I can see the shape of the evaluation. It's still doing this. Put it all in one format code. Stop writing separate lines. Yes, expansion phase and collapse phase. So expansion phase, factorial 5, 5 times factorial 4, 5 times, you see this? This is the space, I guess this is the space-time complexity. Collapse phase. But isn't this like a countdown, right? So this is like a countdown. This is like a countdown, but in our case, we multiply the countdown numbers and we get factorial. How would we write a countdown example in OCaml without the loop using recursion? So it is like a countdown. A countdown using recursion in OCaml can be implemented by defining a function that prints or collects the numbers in reverse order, counting down to 0. Here's how you can write it. Countdown example in OCaml using recursion. So let rec count down n. Base case. All right. So let rec count down n. So let rec count down n is, we need a base case. If n is 0, right? If n is less than 0, then base case return an empty list if, I wouldn't know that. Return an empty list if n is less than 0. Interesting. So if n is less than 0, then empty list. Else n, add the current number and recurse with n minus 1. Oh, he's making a list. I think the double colon means you make a list. Else n, and you cons, or the word is, I think, cons. So you n, and you put together count down n minus 1. So I guess count down 10. So if 10 is less than a 0, then empty list, which is false. 10 is not less than 0. So that means we skip that. We skip the if clause. We go to the else clause. So count down 10. Else 10, count down. We combine. Oh, we are making a list. So n, so we combine. So, okay, n is 10. So we are making a list. This thing will make a list. So 10, we add to count down n minus 1. So 10 minus 1 is 9. So we add 10 to 9, and then we check. If 9 is less than a 0, then this, but we skip that, and now it's 9. And now we, else 9, count down 9 minus 1 is 8. So we add that. But where do we keep the list? So example is count down 5. Look at this. So count down 5 is 5, 4, 3, 2, 1, 0. Right, when I was doing this example in C, I had to use a for loop with the base case and everything, right? Like I is, well, it's kind of similar to the decrementer. We used a decrementer, I minus minus. And if it was, and also we were checking, but now this is creating a list, 5, 4, 3, 2, 1, 0. So count down 10 would create a list. Interesting. But this list, each member of the list is separated by a semicolon. So you see this? Time and space complexity. Use a side effect, print each step. If you want the countdown to print each number, instead of returning a list, print int and print new line, countdown n minus 1. Example, I see. All right. So for the first three steps, the else part of the conditional expression is chosen because the argument a is greater than 1. When the argument is equal to 1, we do not use factorial again, but just evaluate to 1. The expression built up of all the multiplications is then evaluated until a value is reached. This is the result of the whole evaluation. It is sometimes possible for a recursive function never to finish. What if we try to evaluate factorial minus 1? Yeah, it will be a stack overflow. The expression keeps expanding and the recursion keeps going. Helpfully, OCaml tells us what's going on. Stack overflow during evaluation, looping recursion. This is an example of an error OCaml cannot find by merely looking at the program. Yes, that's interesting. It can only be detected during evaluation. This is something what a very interesting tweet from Iceland Jack. He's a I think famous Haskell person, and I wrote like, what is a function? And he wrote a lot of things, but one of the things he wrote is that function is code data. Is not data, it's code data, because you can only inspect it after you apply it. Like after you apply the inputs, or only then you can inspect it. You cannot inspect a structure of a function like data, right? Which is kind of interesting, and this kind of reminds me that because it can only be detected during evaluation. Later in the book, we will see how to prevent people who are using our functions from making such mistakes. One of the oldest methods for solving a problem, oh, this is so mathematical. These are like examples from structure and interpretation of computer programs. I guess too bad. I guess if you only used sum of squares, then it would be. So one of the oldest methods for solving a problem or algorithm still in common use is Euclid's algorithm for calculating the greatest common divisor of two numbers. That is, given two positive integers a and b, finding the biggest positive integer c such that neither a divided by c nor b divided by c have a remainder. Euclid was a Greek mathematician who lived about 3 centuries before Christ. Euclid's algorithm is simple to write as a function with 2 arguments. Now, this function is kind of, I don't know. I think this is a big step compared to, squaring a number. And there's a really nice part in structure and interpretation of computer programs in the video lectures, and they talk about this. That's a really nice part. The greatest common divisor. Yeah, that would be nice to see. One of the oldest methods. I think that'd be nice to see. I can find that and then play it. I'd like to see it. Yeah, I'm back actually. I've just checked the structure and interpretation of computer programs, and the example actually that he uses is the square root. So he's writing an algorithm also from an old Greek mathematician that for the square roots. So it's not for the GCD. So yeah, although it's interesting, yeah, but it's something completely different, which would be also kind of cool to implement. But I know far too little now to even try that, except to play around with ChatGPT. But yeah, let's move on. Let's try to understand the GCD. So again, so one of the oldest methods for solving a problem still in common use is Euclid's algorithm for calculating the greatest common divisor of two numbers. Find the biggest positive integer c of 2a and b such that neither a divided by c nor b divided by c have a remainder. Okay, that kind of makes sense, but again, this is not something that I practice, so it does feel a bit, off. But let's try to, let's try to look at the algorithm and how it's implemented. So we're going to have a let rec GCD AB. I guess that's a good start. Right, even if we don't know how to do it, it's important to start. And I saw that, like, you start writing code and you almost like talk to yourself in the sense, okay, I have this, I have that, but the questions themselves are the code, expressed as code. And then the body of those questions are like, then you work on, on the bodies of the functions. So let's do let rec and GCD A and B. So we can write that, right? So let rec GCD AB, the greatest common divisor, A and B. So now what do? Let rec GCD A and B equals. So if B is 0, okay, again, so this is about the base case. So if B is 0, then A. Right, so the greatest common divisor. So if one of them is a 0, then the greatest common divisor is well, let's say we have A is 2. Let's try again. A is 2 and B is 3. What's the greatest common divisor of A and 2? It's such that A divided by that number and B divided by that number is what? That neither A divided by that number nor B divided that number have a remainder. So the GCD of 2 and 3 is 2 divided by 2 is 1. And 3 divided by 2 is, it has a remainder. So it's only 1. So the GCD is 1. 2 divided by 1 is 2. And 3 divided by 1 is 3. So the GCD of 2 and 3 is 1. Okay. So if we have a 0 divided by, yeah, it won't work. So we just pick the other number. So let rec GCD A and B equals if A, but it says if B is 0. I guess it's the same. If B is 0, then A. What if A is 0? Will that imply B, then B? Else. And now we have to do what? If B is 0, then A. Else. Now actually comes the body of the function. We have to do, okay, it shouldn't have a remainder. That's a sign. It shouldn't have a remainder. So it should be like an OCaml, as we saw before, does integer division and it gives us the number. We would need a mod. I think we would need a mod. It will be like, yeah, we would need a mod. Yeah, A mod B. That's what I know from experience, actually, not more from understanding. So if B is 0, then A. Else GCD B, A mod B. Yeah, I kind of get it, but then I don't get it. So we would put GCD 2 and 3. Let's try this. Is 1. GCD 11 and 12, it's 1. GCD this and this is 1. GCD 5 and 20 is 5. It works. Here is the evaluation. Maybe if we see how it evaluates GCD, yeah. I don't know. I guess this would be also complicated for someone. I don't. Or how the algorithm works. Basically, I didn't know how to write this in OCaml. I'm thinking about it. Let's break down the greatest common divisor and how it's implemented in OCaml. So the function GCD computes the greatest common divisor of two numbers a and b using Euclid's algorithm. The algorithm works based on these key principles. Base case. If b is 0, the GCD is a. This is because any number divided by itself or by 0 results in the number itself. Recursive case. Otherwise, replace a with b and b with a, mod b, the remainder of a divided by b. Repeat until b is 0. Yeah, this thing is not clear. This is too much to unpack for me. When I say replace a with b and b with a mod b, the remainder of a divided by b, it means take two numbers, a the larger number and b the smaller number. Divide a by b and find the remainder when a is divided by b. This is what a mod b means. For example, if a is 48 and b is 18, divide 48 by 18, which gives quotient 2, remainder 12. So a mod b is 12. And a mod b is 12. Update the numbers. Set a to the value of b. Set b to the value of the remainder. b is a mod b. Repeat until b is 0. When b becomes 0, the GCD is the value of a. Oh, this is the thing. You see, it's always, yeah, when I fail to understand, I still don't really get it, but I get it more. When you fail to understand something, it's usually you don't follow up with the recursive call, right? You somehow make some kind of evaluation and you stop and then you say, I don't get it. But you're supposed to take that kind of result and make a recursive call and try to find a way how you keep on applying the thing and lowering the value of the result, or going it up or low. It depends on what's asked. So I guess I have to say it in words. So suppose we want to find GCD 48 and 18. Here's what happens. Start a 48, b 18. So compute a mod b is 48. Mod 18 is 12. Update. A is 18, B is 12. Next step. A is 18, B is 12. Compute A mod B is 18. Mod 12 is 6. Yeah, I don't get it. I still don't get it. only a bit. Even more step by step, using a simple analogy and building the intuition. Think of a GCD like candy distribution. Imagine you have two piles of candies. Pile A has A candies, 48. Pile B has B candies, 18. You want to find the largest number of candies per bag so that both piles can be evenly divided into smaller bags. I see. You want to find the largest number of candies per bag. I see. I have 2 bags of candies. Right. But they are, let's say, 5 or 6 people coming, and I wanted to say children. People coming, or children, and you want to divide the candies so that everyone is happy, right? You don't want them to give, like one kid has more candies and one has less candies, right? You don't want that. You don't want that to happen. So divide pile A by pile B. So take pile A, 48 candies, and divide it into groups of the size of pile B, 18 candies. Well, that's the first thing you do, I guess, right? I would, right. I would take the smallest group, which is 18, and see how many 18s go into 48. So 48 divided by 18, you can fit 2 groups of 18 candies. There are 12 candies left. So this is the remainder, A mod B. A mod B, 48. I see. Wait a second. A mod B. So 48 candies mod 18 is 12 remainder. You see, this is I said the clock thing will help. It does help, but it's not a good example for every situation. When we are looking into GCD, then it's not really a great example. To think in terms of a, monoid. Monoid as in, yeah, okay. I think, that's the name of that mathematical structure of a clock. This is really not... Now it's better with candies in this case. So we have 48 candies in one bag, 18 in other bag. We divide them. It's just you don't think like that. You would say how many 18s go into 48, which is 48 divided by 18, which is 12. Well, the 12 is the remainder. So it gave us 2. So replace and repeat. Now swap the piles. Pile A becomes pile B, 18 candies. And pile B becomes the remainder, 12 candies. Oh. So now how many of 12 go inside of 18? Well, just 1. You can fit 1 group of 12 candies. There are 6 candies left. Replace and repeat again. Pile A becomes pile B, 12 candies. Pile B becomes the remainder, 6 candies. Divide the new pile A, 12 candies, by pile B, 6 candies. 12. Yeah, would I do this? You can fit 2 groups of 6 candies. There are 0 candies left. So how many even bags of candy we have? So the GCD finds us the largest number of candies per bag that allows us to evenly distribute both piles of candies. But if you're asking how many total even bags we end up with, let's calculate that. So you mean we'll have 6 per bag? No, but it depends how many children. How many bags we can make from a pile B? 18. 11 bags. 11 bags? 11 bags? 11 bags with how many candies? Each bag has 6 candies. Yeah, I think I should stop. This is getting too much of it. It's fun. It's like if B is 0, then A, else GCD B and A mod B. Yeah, it's like my mind doesn't... Maybe I should move on. I should pause the video and unpause in a couple of days. How much am I recording? 3 hours and 20 minutes. All right. Finally, here is a simple function on Boolean values. Am I going to quit the GCD? Probably. I'm not going to quit, but wait, it's too much light here. Yeah. Let's just look at it one more time. So A mod B. Yeah, I think it's a lot. I don't get it. I'll have to return to this. I think it's best if I make a pause and I will return to it. I guess that's okay because yeah. Finally, here is a simple function on Boolean values. In the previous chapter, we looked at the and or operators which are built into OCaml. The other important Boolean operator is the not function, which returns the Boolean complement, opposite of its argument. True if the argument is false and vice versa. This is also built in, but it is easy enough to define ourselves as a function of type bool to bool. Yeah, in the previous chapter, I have to read this again. In the previous chapter, we looked at the and or operators which are built into OCaml. So the other important Boolean operator is the not function. Okay, this is a not function. Yeah, I guess the GCD was a bit hard on me. So now I had to reread this again. So the not function, yeah, it's from bool to bool because it's like you're saying not true is from true to false, because not true is false, which returns the Boolean complement opposite of its argument. True if the argument is false and vice versa. This is also built in, but it is easy enough to define ourselves as a function of type bool to bool. So let not x, if x, well, we already had that when we wrote negative, right? Right? So let not x equals, if x true, then, so let not true. So if x is true, then false, else true. So now we have let not true. Let not, well, you could say not to, let not 2 greater than 3. So let not 2 greater than 1. 2 greater than 1 is true, but not true is false. This should be false. Syntax error. Interesting. Yeah, it's like, what do you test this with? Let not true. No, I already defined it with let. I just use not. Not true. This expression should not be a Boolean. Literally, the expected value is bool. Not true. I thought it will show false. Not false. Yeah, and what if I do write not 1 greater than 2? 1 greater than 0. Yeah. So if x, then false, else true. Let not x. We did this. So not true. It doesn't work like that. Let's try again. Let not x is what? If x, what did I write? If true, if x. What did I write before? If x true, then false, else true. If x, then false, else true. He's doing that. So what's the difference? So let not x. So if x is true, then false, else true. Will this be different? Not true. I made a mistake. This is the right way. So if x, then false, else true. Let not x. Bool, false. Okay, well, if, no, not, I guess you could do this, not true or false. So this will be false and not false will be true. Bool, false. Wait a second, not false, bool, true. So I thought true and false would be true or false. True or false, true. So not true, false. Okay. Almost every program we write will involve functions such as these and many larger ones too. In fact, languages like OCaml are often called functional languages. Questions. Write a function which multiplies a given number by 10. What is its type? So the function should multiply a given, okay, that would be not hard. Let mult by 10. Mult by 10. Mult by, let's call it times 10. Times 10x is x times 10, I guess. So times 10, 2 is 20. It's from int to an int. Write a function which multiplies a given number by 10. What is its type? Its type is an int, from int to an int. Right, and when we do show times 10. So write a function which returns true if both of its arguments are non-zero or false otherwise. What is the type of your function? Are there many questions? Write a function which returns true if both of its arguments are true. And false otherwise. What is the type of your function? Write a function which returns true. So we're going to let, how are we going to call it? Both true or false otherwise. What does it mean otherwise? Well, if they're both false, I guess. If they're both true and both false. Is that the exclusive or XOR? Yeah, although it's written if both of its arguments are non-zero. and false otherwise. Oh, well, it's not basically saying that, right? So it's saying returns true if both of its arguments are non-zero. But what does that mean? Like what? Let what do we call it? Return true if both of its are both true. Both true or false. Let's call it both true or false. Both true, both yes or no. Let's call it both yes or no. Both yes or no. Yes or no. A and B. Yeah? A and B. If A and B, if A, I guess, and B, if A and B if A and B are non-zero and false otherwise. So if they are non-zero, so if A and B are if both A and B, if A equals to 0 and B equals 0, then false, else true. Maybe like this. So it's both yes or no. This is a bad name. 2 and 3. Both true. And both yes or no. 0 and 1. Let's try this. True. So this is not good. Returns true if both of its arguments are non-zero. If A is 0, how do you write if both A and 0? Because it's and. And is not working like that, yeah. We have to find a way to write it like explicit, really, both A and B. Maybe we can use not. If A is 0, maybe I could do if both of them are 0. If A is 0. I'll ask ChatGPT how to solve this. My solution so far is this. What did I write? Let be. But it's not good, since when one of them is 0, it still evaluates to true. So you're close, but the issue with your function is in the condition you're checking. So the condition if A is 0 and B is 0 only checks if both A and B are 0. If both A and B are 0, no, and evaluates to false only in that case. However, the problem asks for true if both arguments are non-zero and false otherwise. let me help you correct this. Yeah, there are so many ways to get the result. Let me help you correct this step by step. So here's how you can write the function in OCaml. So let both yes or no a be. If a, this sign not equal, if a not equal to 0, this was too simple, and b not equal to 0, then true, else false. So use a not equal to 0 and b not equal to 0 to check if both a and b are non-zero. Combine the two conditions using the logical AND. So that's all, yeah. Let both yes or no is what? Let both yes or no a and b is what? If a not same as 0 and b not same as 0, then false. Then true, else false, right? If both conditions are true, return true, otherwise return false. Well, it's not saying that. Then true, I did that, yeah, then true, else false. One and two. Unbound, both yes here, both yes or no. Oh, he knows 1 and 2. True, both yes or no. 0, 1, false. It's funny, it's like these very simple examples are so hard. It's just that the mind, somehow they're not hard, but the mind keeps on spinning a bit. And then you almost tend to say, oh, what do you mean? Like I'm trying to build a tool or something and write an OS or like write a malloc in C. And I can do a simple if then if, you know, it's okay. Sometimes you get a thought like that. I do get a thought like that, yeah. Which is again self-defeating. It's okay. Explanation, condition not equal to 0 and b not equal to 0 to check if both a and b are non-zero. So this checks if both a and b are non-zero. Well, I thought AND checks only if one of them. No, it checks if both are true. So combine the two conditions using the logical AND operator, if else. If both conditions are true, return true. Simplified. Yeah. Okay. Write a recursive function which, given a number n, calculates the sum 1 plus 2 plus 3 plus n. What is this type? Oh, we sum a list. So write a recursive function which, given a number n. So we're going to have a let sum, let rec sum list. Let's call it a sum list. Some numbers, some list of num, n. So a sum list of numbers n, a list of numbers 10. So you're going to 1 plus 2 plus, I'm not sure, that's probably not the proper way how to call it, to call this kind of a function. So the sum of 1 plus 2 plus 3 plus n, what is its type? So sum list, so it will be n, right? It's almost like the way how you build a list. So it will be n plus what? 10 plus, are we going to go back? The base case, we're going to need a base case again. Otherwise it won't stop. The recursive call will not stop. So it should stop at 0, right? If n is 1, then 1. right? Else n plus but it will be done in reverse, right? I just want to do now m plus sum list of num n minus 1, because okay, if we do sum list of num 10, so if n is 1 then 1, right? So it's not the case, so we move here, right? So 10 plus sum list of none 7 minus 1, that's 10 minus 1 is 9, so 10 plus 9, and then it's not here, and 9 plus 10 plus 9 plus, so it's 10 plus 9, and then n plus sum list of noun n plus again 9 plus, right? And then 9 plus, it just builds up, it expands, and then it will collect. So 10 plus 9 plus 9 minus 1 is 8, and then 10 plus 9 plus 8 plus 8 minus 1 is 7, all the way up to 1. When it gets to 1, then 1. So will this work? Sum list of num 5, 15. 5 plus 4 is 9, plus 3 is 12, plus 2 is 14, plus 1 is 15. So sum list of num 100 is 5050. All right, that's correct. Yeah. What is the type of your function? What is its type? It asks, give its type. You see, always check the type. I think I didn't check the type of the both. Wait a second. Show both yes or no. Int from int to bool. All right. And this one, show sum list of num. Sum list of none, int to int. For ints, it's from int to int. Okay. Recursive function, right? Write a function power x n, which raises x to the power n, give its type. Well, this kind of looks too simple. Power xn. Let power xn equals what? Which raises x to the power of n. Oh, it's x times n. No, this is recursive. Because let's say I have, right? Let's say we have x is 2 and n is 4. So that means 2 times, it's not 2 times 4. It's 2 times 2 times 2 times 2. So it's 2 times itself 4 times. So that means I have to use a recursion. Let rec power xn. Let rec power xn. Yeah, this should be a recursion. So, okay, we're going to have an x times, right? And then this n x times power xn. So let's say it's 2 again, power xn, 2, and we have a 3. So 2, you multiply 2 by itself 3 times. So, but n tells us how many times. Power xn. If n, well, we should have a base case. The way to stop then, right? Always when we do recursion, we have a base case. So the way to stop. So when, oh gosh, my mind is it's not working now. Maybe it's too much already. How long am I doing this? 3 hours and 46 minutes. It's almost 4 hours of OCaml. And I'm still at very basic things. Let rec power xn. X times. I need help with this. Yeah, so or maybe I should stop. Write a function power xn which raises x to the power of n, give its type. Let red. I don't know, let's look at it together. Skip. No, well, we have a base case, I guess. If what? If n is, yeah, how many times? If n is 1, then 1. That's the end. Else power else x times power n minus 1. Again, we're doing it, right? Because power x. Power x n minus 1. No. Power x n minus 1. Will this work? Power x n minus 1. But what power? It doesn't know that we multiplied. So it has to have an x times n power n minus 1. I guess I'm confused because power takes 2 arguments. Of course. Let reg power xn. It was wrong of me to try this. If n is 1, then what? if n is 1, then x. No, if n is 1, then x. Otherwise, x times power x times n minus 1. I think this is also wrong. Let rec power xn equals, if n is 1, then x times x, then x times n. Else power x n minus 1. This is right. Power 2 to the third is 2. X times. Maybe it's let rec power xn. If n is 1, then x times n, right? Else power x times n minus 1. If n is 1, then let's say n is 1, 2 to the 1, then 2 times 1. Okay, that's correct actually. Let's let power xn. If n is 1, then x times n, right? Because 2 to the 1 is 2. Else, but what if we have 2 to the 2? So we have to 2 times 2. Else, n is not 1, right? So n is not 1. N is not 1. We should probably put the case of if n is 0, because then the result is 0. Can we like, yeah, I'm curious now, can we have more than one else branch? If n is 1, then x times n, right? And else power x or maybe we don't have, are we going to call it, is it recursive? If n is 1, then x times 1. Else, let's try this, x times n minus 1. But this will not work. I thought I have to call it, you know, like power, right? Like power 2 and 3. It's 4. Yeah, it doesn't work. 2 times 2 times 2 is not 4. So let's try again. Let rec power xn is, if n is 1, then x times n. Else x times, I guess x times power x n minus 1. N minus 1. But I guess this is wrong because we still don't know what power x n minus 1 does, right? This is not... This is correct. 2 to the 2 times 2 is 4 times 2 is 8. Power 5, 6. Yeah, this is correct actually. So if n is... Yeah. Explain. This function calculates where x is the base, n is the exponent. If n is 1, then x times n, else x times power x n minus 1. So the base case is if n is 1, then x times 1. The recursion stops. The function directly computes x times 1 and returns x. This is the base case of the recursion, recursive case. Else x times power x n minus 1. When n is greater than 1, the function multiplies x by the result of calling itself with n minus 1. This keeps reducing n until it reaches the base case. Second call 2 times 2, power 2 times 1, collapsing, yeah. There is a subtle issue with the base case. This works for positive exponents but is slightly unconventional because the base case n is 1 doesn't return x directly. Instead, it calculates x times 1. To make it mathematically cleaner and support 0, which should return 1, we can improve the function as follows. If n is 0, then 1. Okay, else x times power x n minus 1. Time complexity. Okay. Write a function is constant which, given a lowercase character in the range from a to z, determines if it is a constant. Okay. I'll make a short pause.